Mathematics of graphs. So what is graph theory? So graph theory deals with relationship between objects. So these objects are represented by dots or points, which are technically called vertices, while objects are related if there is an edge represented by a line, segment, or curve that connects them. So graph is a set of vertices. So vertices are points and dots, and edges, which are line, segments, or curves. So here are some examples of graphs. Look at number 1. So we have here 4 dots, so that means 4 vertices, with also 4 edges, which are these line segments. So if there is a line segment or a curve which connects 2 dots, that means that these 2 objects are related, or there is a relationship between these 2 objects. So just like A and B, A and C, B and C, C and D. But if there is no line segment or curve that connects them, that means that they are not related, just like B and D. So there is no edge, line segment, or curve which connects to them. Number 2, so A here is connected to B, B is connected to C, C is connected to D. So look at the edges. The first 2 are line segments, while the third one is a curve. Then for number 3, so you have here 5 vertices. So you have A, B, C, D, and E. Then A is connected to B, B is connected to E, to C. Look at D. There is no line or curve which connects D to any object. So that means D has no relationship or is not related to the other vertices. So here are some basic terms used in graph theory. First is the degree of a vertex. So degree of a vertex, it refers to the number of edges that emanate from that vertex. Examples, look at this first graph. So you have 4 vertices, A, B, C, and D. So for vertex A, the degree of this is the number of edges that emanate from this vertex. So let's count. This is 1, 2, and 3. So that means the degree of vertex A is 3. Look at B. There's only 1. So that means the degree of vertex B is 1. C, it's also 1. D, it's also 1. While on the second example, so you have 4 vertices. Degree of A, so you have 1 and 2. So that's 2. Degree of B, that's also 1 and 2. So the degree of B is 2. While for C, you have 1, 2, 3. So the degree of C is 3, while for D, we have 1. So the degree of D is 1. So just count the edges that emanate from that specific vertex. So next is walking a graph. So for walking a graph, it is a movement from one vertex to other vertices passing through their edges. Example, so for this graph, you have again 4 vertices and 4 edges. So out of this graph, I have some example of a walk from this graph. So A, B, C. So there's a walk, or it is a walk from A to B to C. So there's a movement from vertex A to the other vertices passing through their edge. So when you do a walk, make sure that there is an edge between the objects. So look at B to D. If B to D, you cannot make a walk from B to D since there is no edge between them. So make sure that there is an edge when you do a walk or when you do a movement from one vertex to another. Another example of a walk from this figure is B, C, and D. So you have B to C to D. Here, A, B, C, and D. So from A, so a walk from A to B to C and to D. So there are a lot of walks from this graph. So as long as there is a movement from one vertex to other vertices passing through their edge. So that is for a walk. Next is circuit. So for circuit, it is a walk, so that means a movement from one vertex to the other vertices, but it must start and end on the same vertex. So for a circuit, there is a movement and you should start and end on the same vertex. So if you start with vertex A, you also have to end with vertex A. So example, A, B, C, D, and A. So from A to B to C to D back to A. So it started with A, it also have ended with A. Another example, D, E, C, D. So from D to E to C and to D. So it started with D, it also ended with D. Next, A, B, C, E, D, A. So from A to B to C to E to D back to A. Another example, B. So B to C to E to D to A to B. So it started with A, but also, and it started with B, it also ended with B. So still, there are a lot of circuits that you can get from this figure. These are only examples. So next is Eulerian circuit. So take note, it is a circuit, so that means you have to start and end on the same vertex that traverses all edges only once. So for Eulerian circuit, you have to start and end with the same vertex. Then you need to traverse all the edges only once. Take note of the only once, all edges. So example, you have here A to B to C to E to D to C and to A. So it started with A, also have ended with A, and it has traversed all the edges only once. There should be no repetition of an edge. Then here you have C to E to D to C to A to B back to C. So it started with C, also have ended with C, and it has traversed all the edges once. So next is the Eulerian circuit theorem. So according to this theorem, a graph is Eulerian if and only if all vertices of the graph are of even degrees. So this theorem means that not all graphs have Eulerian circuits. So only those graphs whose vertices are all of even degrees. So if we go back to this example, so look at the degrees of all its vertices. So A, so the degree of A is, that's 1, 2, so that's 2. B, 1, 2, so that's 2. C, 1, 2, 3, 4. So the degree of C is 4. For D, 1, 2. So the degree of D is 2. E, 1, 2. So all of its vertices have even degrees. So that means, or that is the reason why we are able to get a Eulerian circuit out of this figure. Note that these two Eulerian circuits are only examples. You can still find a lot of Eulerian circuits out of this figure. Look at this graph above. Let's check the degrees. Degree of A is, that's 1 and 2, so 2. B, 1, 2. D, 1, 2, 3. So the degree of D is 3, and that is odd. So that means not all of its vertices are of even degree. So you cannot find a Eulerian circuit out of this figure. So, if you are asked to give a Eulerian circuit out of a given graph, first thing that you need to do is to check its vertices. So, if all of its vertices are of even degrees, that means that you can find a Eulerian circuit out of that figure. But if not all of its vertices are of even degrees, then you cannot find a Eulerian circuit out of that graph. So just like this one. So here, not all vertices are of even degrees, so you cannot find a Eulerian circuit out of this figure. While for this one, all of its vertices are of even degrees, then you can find a Eulerian circuit out of this figure. Next is the Eulerian walk. So it is a walk in the graph, traversing all edges once without returning to the starting vertex. So for a walk, so as long as there's a movement, so no need to start and end with the same vertex. While from the word Eulerian, that means that you need to traverse all the edges only once. So look at this figure. So again, you need to traverse all edges once, then no need to return to the starting vertex. So for this graph, or for this example graph, you have the Eulerian walk out of this figure. So A goes to B, to D, back to A, to C, E, D, E, C, B. So again, you have A to B, to D to A, to C to D, to E, C, B. So it started with A, it ended with B, and it has traversed all the edges of this graph. So again, this is only one example of a Eulerian walk out of this figure, but you can get a lot of Eulerian walks out of this particular graph. So next is Hamiltonian circuit. So again, it is a circuit, so you need to start and end with the same vertex. Then this is Hamiltonian. So it talks about vertices. So for Hamiltonian circuit, it is a circuit visiting all vertices once. So back in Eulerian, it talks about edges. So you need to traverse all edges once. But for Hamiltonian, it talks about vertices. So you need to visit all the vertices once. So for this figure, examples of Hamiltonian circuits out of this figure are this. So let's look at the first example. So you have A, so from A to B to C to E to D to A. So since it is circuit, so it started with A, also have ended with A, and it has visited all the vertices. Next example, so from C to E to D to A to B to C. So it started with C, it also have ended with C, and it has visited all the given vertices. Then another is E, so from E to C to A to B to D back to E. So again, it started and ended with the same vertex, which is E, and it has visited all the vertices. So finding a Hamiltonian circuit out of a particular graph is a bit easy since you will only consider the vertices. But what if there is a measurement in every edge of the graph? So for instance, this example, so note that it's not to scale. So from A to B, the distance from A to B is 10. The distance from A to E is 12. The distance from D to E is 29. So there are distances between the objects, or there's measurement on every edges. So if you're asked for Hamiltonian circuit, you can easily get or provide a Hamiltonian circuit out of the figure. So from this example of Hamiltonian circuit is here. So from A to B to C, to C to D to E back to A. If you add all those edges that you have traversed, so that's from A to B, so that's 10 plus B to C, that's 8. C to D, that's 5. To E, that's 29. Back to A, that is 12. The sum of all those edges is 64. So let's try another Hamiltonian circuit out of this figure. So from A to B to that's 10. Then B to D, so that's 12. To E, that's 29. To C, that's 8. Back to A, that is 20. And that total, or that sum, is 79. So the measurement now is a bit higher, or it's higher than the first Hamiltonian circuit. Another Hamiltonian circuit out of this figure. So C to B, so that's 8, plus to A, that's 10, plus to D, which is 10, to E, which is 29, back to C, which is 8. The sum of those edges that you have traversed is 85. So it goes bigger. So how are we going to find the shortest Hamiltonian circuit out of this figure? So one method is by the greedy algorithm. So with the help of greedy algorithm, you can find the shortest Hamiltonian circuit out of a particular graph. So the first step here is to find the shortest edge. So you start with the shortest edge. So what is the shortest edge here? It's D to C. So the measurement is only 5. So you start with D to C. So we have here D to C. So we are now on C. Then next step, on the end vertex of that edge, pick a not yet chosen vertex with the shortest edge. Repeat this step until all vertices are chosen. Then go back to the starting vertex. So again, from the first step, we have the shortest edge, which is D to C. So we are now on C. So from this edge, from this vertex, we will try to look for the shortest edge, which is not yet chosen. Because if you are on C, its distance from C to A is 20, to B is 8, to D is 5, C to E is 8. So this is the shortest, but we are already done with D. So we need to choose the vertex which is not yet chosen. So the shortest here is B and E. It has the same distance, which is 8. So it's your choice if you want to go to B or you want to go to E, since they have the same distance. So let me choose E. So we are now on E. So from D to C, we are now on E. So from E again, you need to look for the edge with the shortest measurement. Again, it must be a vertex which is not yet chosen. So from E, we are done with C. So E to A, the distance is 12. E to B, that's 14. E to D is 29. So the shortest here is this 12. So that means from E, you will go to A. So from E to A. So we are now on A. Then again, you need to look for the shortest edge. So A to B is 10. A to D, so we're already done with D. So A to E, we are also done with E. A to C, we are also done with C. So we have no other choice but to go to B. Then this is our last vertex to be visited. So we are done with D, C, E, A, last is B. Then since this is the last, you need to go back to your starting vertex, which is D. So if you will add the measurements of the edges, so from D to C, so that's 5, plus C to E, that's 8, plus E to A, which is 12, A to B, which is 10, B to D, which is 12. The sum is only 47. So try to compare this 47 to our previous Hamiltonian circuits. So it's way shorter than the other Hamiltonian circuits. So you can, or the greedy algorithm is an effective way of finding the shortest Hamiltonian circuit out of a particular graph. So let's have another example. So it's problem. It's entitled, "It's More Fun in the Philippines." So suppose you are a foreigner planning to visit the Philippines for a vacation. So you are planning to go to the following places. So Manila, Davao, Bohol, Cebu, and Boracay. So now you want to know what itinerary would be the best for you. So which among these places should you visit first, then what's to follow, and so on. So we have here the map of the Philippines, and let's identify the places that you're planning to visit. So you have Manila, Boracay, Cebu, Bohol, and Davao. So out of this map, let's use graphs to represent these places as objects and the distances between these places. So I have here the graph. So you have the Manila, Bohol, Davao, Boracay, and Cebu. So with the help of the internet, I come up with the distances between these places. So Manila to Cebu, that's 570 kilometers. Manila to Boracay, 309 kilometers. Manila to Davao, that's 978 kilometers. Manila to Bohol, that's 618 kilometers. So these are actually air distances. So it's by plane. Then Bohol to Cebu, that's 72 kilometers. Bohol to Boracay, that's 344 kilometers. Bohol to Davao, that's 346 kilometers, and so on. So I have here the distances between all these places. So going back to greedy algorithm, the first step there is to find the shortest edge. So the shortest here is Bohol to Cebu, which is only 72 kilometers. So we have here Cebu to Bohol. So you will start with Cebu, then from Cebu you go to Bohol. So next step, from Bohol, look for the shortest edge and with an unchosen vertex. So from Bohol to Manila, that's 618 kilometers. Bohol to Cebu, we are done with Cebu. Bohol to Boracay, that's 344 kilometers. Bohol to Davao, that's 346 kilometers. So the shortest from Bohol is Boracay. So from Bohol, you will go to Boracay. So we have here Boracay. Then from Boracay, again you look for the shortest edge. So Boracay to Cebu, that's 282 kilometers, but again we're done with Cebu. Boracay to Manila, that's 309 kilometers. Boracay to Bohol, we're done with Bohol. Boracay to Davao, that's 678 kilometers. So we are to choose Davao or Manila. So the shortest or the shorter distance is Manila, which is 309 kilometers. So from Boracay, we will go to Manila. So we are now on Manila. Then we are done with the 4 places. So we're done with the other places. So we need to go to Davao as our um, last place to visit. So we have Davao. Then since it is a circuit, you need to go back to your starting vertex, which is Cebu. So that means you will start with Cebu. Then from Cebu you will go to Bohol. From Bohol you will go to Boracay, then to Manila, to Davao, then back to Cebu. So this is the shortest path or the shortest itinerary that you can have if you plan to visit all these 5 places in the Philippines. So the references.